Well, let me just thank you for inviting me. I literally arrived less than an hour ago, so I hope this will be coherent. In correspondence with Vanderlei, it seemed to me that what is interesting, we both thought it'd be interesting to spend some time on correlation functions. So I plan to spend the first 3 talks on correlation functions, and let me write down what I hope to cover. This is X-ray scattering, neutron scattering, and finally linear response. These would be the many body things. The X-ray scattering is stuff I've done in electromagnetism classes, but it's not in our many body book. The neutron scattering I've done when I've lectured on solid state physics or liquid helium, but it's again not in our many body book. This is from the many body book. So this actually gets into the guts of a little bit of quantum field theory, although it's not the nice thing about linear response theory is it kind of magically ends up with a correlation function. And particularly if you study the behavior of a magnetic system, you end up with a correlation function of 2 spin densities at different space-time points. And you can measure that as a generalized susceptibility, and this has been done experimentally. If you deal with density variations, for example, neutron scattering, or if you apply a localized pressure, you can create density waves, and then you end up with a linear response theory that involves a correlation of, it's a retarded commutator of 2 densities at different space-time points. And I'll talk about that. And when you take, if it's an extended system, and you take a Fourier transform, then you end up with a susceptibility, a generalized susceptibility, which depends on the wave number and the frequency. And then by taking various limits, you can compare with nice experimental things. X-ray scattering basically measures things at equal time only because the X-ray doesn't have the energy information. Neutron scattering measures functions of both the wave number and the frequency, which is why it's so powerful in studying dispersion relations in solids or in liquid helium. And that'll all come out from the linear response. So after I've done that, then I want to come back to the Bose gas. Oh, this one's...
No, I'm afraid you have to hold it down this way.
Okay.
Not this way, otherwise the ink doesn't... No, it's...
Well, I can. I'm left-handed.
Yeah, this way, that's right.
Shake the hands.
That's the Bose gas, and I want to give 2 talks on that. One, I'll talk about the ideal Bose gas in a box and in a trap. And then I want to talk about the Bogusubov theory of how you put interactions, at least in the case of a box. And that'll be one lecture. And then the second lecture, I wanted to talk about what happens when you put the Bose condensation and the interactions in a trap. And that's much more interesting. That's the one that's experimentally interesting. Many of you have probably studied this, but I hope there'll be some insights that you will find interesting. So let me now start on talking about X-ray scattering. What I imagine is I have an electric field, E, which is a function of R and T, and I'll write this as some E naught, some polarization, epsilon, e to the I, k dot R minus omega t. And this is an incident plane wave that comes in like this, and then it will scatter. And initially, I want to just study a scattering. This is K. This is K prime. Initially, I want to just study a single electron at R0. So when this interacts with the electron at R0, you just evaluate this at the point R0, and that tells you the incident electric field that acts on it. So you get an electric field at R0, which is this E0 epsilon e to the I k dot R0 minus omega t. Now, this electric field acts on the electron, and so the force is minus E times all this. And then I want to assume that the electron moves a little bit. So its position is r0 plus some small amplitude a of t, which tells you how it moves. Like that. And I want this to be small. Basically, I want the amplitude of this to be small compared to the wavelength of the incident radiation, so you can use a dipole approximation. So we assume that k times the magnitude of A is small. Now, the acceleration, this is a constant, but the acceleration is just minus omega squared times A, right? So the acceleration, so Newton's law says you get minus omega squared times A, and you multiply by m, and you equate that to minus e times this, and you end up with a formula for the acceleration. No, you end up with a formula for the amplitude. You end up with the amplitude A as a vector is E0 epsilon. You can cancel the common factor of the frequency, so you get e to the I k dot r0. And in the denominator, you get m omega squared. Now, the interesting thing you can see, if omega goes to 0, the amplitude diverges, which is just the DC case. If you apply a DC field to a charged particle, it moves arbitrarily far. So it's the fact that it oscillates and cuts off as you move back and forth, and that gives you the 1 over omega squared. It's in the direction of the polarization, which is what you would expect. And as I say, I'm assuming the amplitude of this is much less than the magnitude of k. Now, from this amplitude, you can work out the dipole moment, because P, the dipole moment, is just minus E times A. Okay? And so you put this in here and you multiply this all out, you get a minus E. And this is then, you get the magnitude of the dipole moment. It has all these factors with a minus E in front of it. So it goes like E squared. Now from P, you just go back to your E and M book and work out what, if you have an oscillating dipole, it radiates. And from that you can calculate the electromagnetic field given the oscillating dipole. It has this characteristic donut shape. It's 0 along the direction of the oscillating P and is maximum in the equator in the horizontal plane. And you can work out all of this, the radiation from this oscillating dipole. And you get to, eventually you have, I mean, I'm not going to go through all this, but you work out the Poynting vector, which is the energy flux of the oscillating dipole. You divide by the energy associated with the incident beam, and that gives you a cross section. And so you get this cross section in the usual way. And what you end up with, and this is, I think, a standard calculation, d sigma d omega prime is equal to RC squared times some angular factors, which I'm not so interested in, but these just depend on the geometry between this vector and this vector. Now, the RC is just what's called the classical radius of the electron. You just say that the energy at a, you have a charged particle, the self-energy at a distance RC is defined by setting that energy equal to mc squared. And so you say, let's see, E squared over 4 pi epsilon naught RC is equal to mc squared. And then you solve for RC, and you find that RC is approximately 3 times 10 to the minus 15 meters. It's the order of a couple of Fermis. It's the size of a nucleus. It's a nuclear size. And so the order of magnitude of scattering from a single electron is always of order the classical electron radius squared times some angular factors. And if you integrate over the angular factors, you get an answer which depends on your assumption about the polarization. If the incident radiation is unpolarized, then you say it's a linear combination of a polarization like this and a polarization like this, and you have to sum over both states, and that gives you the classical Thomson cross-section that Thomson calculated many years ago. And for the Thomson cross-section, you get sigma total for the total cross-section is 8 pi over 3 times RC squared. And that gives you the total scattering by a single electron for an unpolarized radiation. And if you assume the radiation is circularly polarized or linearly polarized, the numerical factor is slightly different, but you always end up with this very characteristic factor, RC squared. So that's the order of magnitude of scattering from a single electron. And of course, that's hard to see because it's such a very small cross-section. Qualitatively speaking, you can think of a little sphere of radius RC, and basically all the energy incident on this little sphere is removed from the incident beam and is scattered. And what you're measuring in the total cross-section is how much of the original energy is taken away from the incident beam and dispersed in various other directions. Okay? So I'm sure you've seen this in electromagnetism classes, but now what's interesting is what happens when you have an assembly of free electrons. So you have a whole bunch of free electrons. And now you can do it this way, but it's more useful from my point of view to go back and think about what's the total induced current from a set of free electrons. So what happens if you have a set of electrons at Rj, which is a function of time, then each of these electrons is going to oscillate. And there is an induced current. And so what you end up with is an induced current which has a simple and intuitive form. The current density, J of R and T, is minus E, the charge on the electron. I'm going to leave this picture because I'm going to need it in a minute. Then you get a sum on all J from 1 to n over every electron in the system. There is an induced amplitude, which I'll call V sub j, which tells you about the velocity of each electron. And because this is a current density, you get a set of delta functions at the position of each charged particle. So you get a delta, three-dimensional delta function of R. This is the position that we're trying to measure at, minus R sub j of t. Okay? And this is nice because this will turn out to be easy to manipulate when we try to put it all together. So a typical number density is just, instead of j, you have number density. You don't have a minus e and you don't have a factor vj in front. You just have a sum over delta functions that tells you where all particles are. And you can think about that if you take the sum over delta functions and integrate over a very small volume. All the delta functions that are inside that volume contribute, and all the delta functions that are outside that volume don't contribute. And so for the number density, you end up with the total number of particles that's in that little volume. And that's just what you mean. The number density is the number of particles in a volume divided by the volume. And so this is just a generalization to a current density where you take the same set of delta functions, but you multiply by the amplitude of the motion of each particle. And that's just, this is it would be minus I omega times this, because this has a factor e to the minus I omega t to it implicitly. And so that would be the velocity of each particle. And then you just put in a factor of minus e to take account of the fact that this is supposed to be the electric current density. Okay? Does that make sense? The reason I like this approach is we have a well-defined formula from classical electromagnetism that tells you if you have a current, you know how to calculate the vector potential just by solving Maxwell's equations. Just as in electrostatics, if you know the charge density, you can write down the electrostatic potential there is a Lorentz invariant formulation which tells you if you know the charge density and the current density, you can write down the scalar potential and the vector potential as an integral over the outgoing Green's function, which is e to the ikr over r, or kr minus r prime over r minus r prime. So you get a well-defined formula that you can look up in Jackson that tells you what the vector potential induced by this current, and this current is induced by this incident field. So in the end, you end up with a vector potential that's proportional to these factors, but you end up with a sum over all the different charge particles, which is a very useful way of thinking about it. And the formula, the Jackson formula, or whatever book you like for E and M, is you get A of R and T is mu 0 over 4 pi times an integral dv prime over all the volume where these electrons reside. And the integral only extends over a localized region. And then you get this outgoing wave thing, e to the I k times the magnitude of r minus r prime divided by r minus r prime. And then you just get j of r prime. Okay? That's just the standard formula from Jackson. And mu naught is the permeability of the vacuum. And these are just using SI units, which I think most people probably are accustomed to. Now, this is completely general, but it's so general it's not so helpful. And so if you have a localized source, the integral runs over the localized source, but I want to go way far away, r, so I want to do my observation at r, which is way away from the localized source, and so I can expand r is much bigger than r prime. And you can expand this out using just algebra, and this becomes approximately mu 0 over 4 pi. You get the outgoing wave e to the I kr over r. From taking the leading term of this is just e to the I kr, and you get an r in the denominator. But then you have to be careful about the interference from the next term up in the exponent. And so what you end up with is an integral dv prime e to the minus I k prime dot r prime. And when r prime is the observation point, that was the integration point, times j of r prime. Okay? So I've just expanded this to give you this factor, which is just the outgoing wave that's localized at this point, times this has the interference of all the different contributions. Now this doesn't look very promising, but because you have a sum of delta functions here, if you substitute this in, you can actually do all the integrals because you have a three-dimensional delta function, which allows you to write it in this simple form. Because you just do this integral term by term over all the different electrons in the system.
So why I don't have time there? When I have this long
Oh, it's because the position here depends on time. You're right, J should be a function of t. And the t comes because the electrons are moving. Okay? And you're right, that's important. But I sort of suppressed it because it's a lot of writing out. And so if you substitute this in here, you get that A is approximately minus E mu 0 over 4 pi. You get the outgoing wave e to the I k r over r. You get a sum on j equals 1 to n. You get v sub j, which is this amplitude, times e to the minus I k prime dot rj, and this is a function of t. Okay, so that's where the time comes in.
Not only from that, from Vj also, depends on time.
Yes, you're right.
According to the frequency.
You're right.
of u.
You're right. It's just I suppressed it, but you're right, exactly. And now, for classical scattering, the assumption is that the induced oscillation is at exactly the same frequency as the incident wave. Now, that breaks down when you get to the Compton effect, but we're not talking about that kind of high-energy X-rays. We're talking about X-rays with typically wavelengths the order of an interparticle spacing, which is, to get the Compton wavelength is 2 orders of magnitude smaller than that, as I remember. So I'm not going to worry about the quantum effects. And so what that means is the magnitude of K prime is exactly the same as the magnitude of K. The magnitude of the scattered wave is the same as the magnitude of the incident wave. Okay, so this K prime has a different direction, but it has the same magnitude as the K that comes in here. All right? Now, this Vj, as you pointed out, is directly proportional to the incident wave. So it has this frequency dependence, and it has an e to the I k dot r sub j. So if you put this in, you get e to the I k dot r sub j, you get e to the minus I k prime dot r sub j. And so what you end up with is, and now let me write this down here, a of r and t. Well, because everything depends on this common factor e to the I omega t, I can throw it away. So I'm going to now suppress the t and just write it a of r. And I'm being a little careless about all the factors because I don't need them. E to the I k r over rc. You get an e naught epsilon. You get a factor that I'm going to call f of k prime. And then I get sum on n, sum on j equals 1 to n e to the I k minus k prime dot r sub j. Okay, and in the assumption that this is a weak field limit, I've been able to cancel the e to the minus I omega t, which is a common factor that every term has. Okay? Now, this is just the usual outgoing spherical wave for an outgoing spherical wave. This just says that the vector potential induced is proportional to the magnitude of the applied field, and it's polarized along the direction of the applied field. This factor is called the scattering amplitude, and it only depends on the property of a single electron. It tells you, and this is the Thomson thing that goes into the Thomson cross-section, it tells you if you have, say, unpolarized electromagnetic energy on a single electron, it scatters to some direction k prime, and this tells you the details of that one particle scattering. And that's something that is well known back in the 19th century. So the interesting factor is this, which has all the effect of the collection, the many-body physics of the collection of electrons. So all the many-body physics is in this particular factor, and this is the one I want to focus on. Because that's the thing that's of interest, not just for electromagnetism, but this is the basis for all of X-ray crystallography. Because you want to study the interaction of these outgoing waves and the incident waves between all the different particles. You notice if there's only one particle, this you can always take as just a phase factor. But when you have a whole bunch of particles, the interference becomes crucial. And so that's why this is so interesting and important. And typically this scattering amplitude, again, has the dimensions of this classical electron radius, because when you square it, it's going to give you this kind of factor. So the scattering amplitude has the directions of a length, which is the order of the classical electron radius, which is a few times 10 to the minus 15. Now let's just, to see how this works, let me first of all come back to just a single electron and apply this for a single electron and show you how you get the answer, because I don't want to go through it for many electrons, but it's the same thing. So if we just have a single electron, I can put the electron at the origin, therefore this factor goes away, and you just get this. So A is going to look like this outgoing wave, E naught epsilon times F. Now B, you remember B is just the curl of A, and we want B for the scattered wave because that's what you measure at a detector. So if you work this out, the curl of this in the long distance limit just goes like, this will be I k prime cross A. And A has this epsilon in it. So apart from factors, this is going to go like k prime cross epsilon, the unit vector for the polarization of the incident wave. And now you need to calculate, out here you need to calculate the Poynting vector, which is E cross H, or factors E cross B. And then you calculate the total energy that comes out here. You divide by the incident energy, and what you get is the differential cross-section, d sigma d omega prime, for a particular polarization. And it goes like the absolute value of F squared. F typically can be complex if you have circular polarized radiation, say, for example. And then you get a single factor k prime cross epsilon squared. And so this tells you all about the scattering, the magnitude, and this tells you about the polarization. And it's this factor that gives you this typical dipole radiation. But if you study the behavior of unpolarized radiation, there are tricks to do these sums over polarization. And if you do the unpolarized, you average over polarization states and integrate over angles, you get back to this answer. And that's all in Jackson if you want to read about it. So what's interesting now is to come back and forget about this one particle thing and come back and look at this thing. And so at the end of the day, if you repeat this process, you're going to get all these same factors, but then you end up with the absolute value squared of this quantity. And so that all the information about the electrons in the many-body system is contained in this factor. So now let me focus on this factor, because everything else you can just do using classical electromagnetism. But in order to calculate this, you often have to revert to quantum mechanics. And so that's why this is so interesting. And next time I'll talk about the neutron scattering, which is more subtle and more interesting, because the energy, you have energy resolution for a neutron that you don't have for X-rays. Basically because the scattered X-ray in these limits always has exactly the same frequency as the incident X-ray, because you're using classical electromagnetism to determine the dipole radiation. And so the induced dipole has exactly the same frequency as the induced radiation. And therefore, you don't see any measurable energy shift. Now let's come back and look at these two things. It's convenient to define, let me erase this now, because I'm not going to go through the electromagnetism calculation again. It's straightforward, but it's just tedious. So it's convenient to define Q as K minus K prime. And therefore, what this factor is sum on n, on j, equals 1 to n, e to the I, q dot r sub j. Okay? Now, q is basically this vector. And we're only going to be usually interested in the magnitude of it. And because if this is an angle theta, no, it's not, my drawing's wrong because of the minus sign. So you have to do this drawing. You have k, you have this is k, you have minus k prime, and this vector is q. Okay? And if theta is equal to 0, then these vectors are anti-parallel to each other, and you get q equals 0. If theta is pi, which is the maximum it can be, then this angle comes out like here, and q is twice k. So the general formula for q is that it's 2k sine of 1/2 of theta. And so if theta is equal to 0, then q is equal to 0, which is forward scattering. If theta is equal to pi, then this is 1, and q can be as big as 2k. So although in principle you need this factor for all q, you can't measure it for all q because q can't be bigger than twice the incident wave number. But if you need it, you can try to go to shorter wavelengths, which will give you a little more information. But that's a limitation. You don't have this thing well known for all values of q. You only have it for values of q that are given by this region, this equality. But that's okay. H bar q as a vector can be thought about as the magnitude of the momentum that's transferred to each electron. Okay? And so you determine the magnitude of the momentum that's transferred. You choose the k that you're going to put in here, and you choose the angle. And you vary the angle, so you study the behavior, what happens when you make a very small momentum transfer h bar q to the electron, or you can make a large momentum transfer h bar q to the electron, but it can't be bigger than 2k with a factor of h bar. That's just the rules of the game. But you still get a lot of useful things out of it. Okay, so if you take this formula and now repeat all the E and M, the electromagnetism, you know A, you can take the curl of A to get B. From B, because way out here it's a plane wave, you can calculate E. From E cross B, or E cross H, you can calculate the Poynting vector. So you know the energy flux out here. You know the incident energy flux because you know the form of the plane wave, and you can get d sigma d omega prime, where omega prime refers to the solid angle of the scattered beam. And what this is d sigma d omega prime for one electron multiplied by the absolute value sum on j equals 1 to n e to the I q dot rj squared. So all the information that you get from this result is contained in this factor, because this is just the behavior for a single electron that I erased before, but this is a straightforward thing you can look up in Jackson, or Landau and Lifshitz gives you a whole bunch of really elegant tricks to do the sums over polarization. It's very elegant. It depends on the statement that if you have a one linear polarization like this and another one like this, then epsilon 1, epsilon 2, and k form a linear triad, and they're a complete set. So sums over direct products of epsilon 1 plus epsilon 2 is a delta Kronecker delta minus k dot k as an outer product. And so that's a trick that's really helpful, and I don't remember whether Jackson teaches you that. But Landau, it works for circular polarized light as well, because if they're circularly polarized, they're still linearly independent states, and they plus the k vector forms a triad in some sense. They form a complete set of states. So if you ever need to do these sums over polarization, go to Landau and Lifshitz. It's hidden in some footnote somewhere, but it's very helpful. Okay, so this is the most interesting part. Everything we were interested in is this product of the absolute value of this sum, or e to the iq dot r. So everything that you can ever measure about X-ray scattering from a solid or a liquid is contained in this factor. Now you notice it's manifestly real. So you lose a lot of the phase information in X-ray scattering. You don't have the phase information. That's called the phase problem. And people have developed all sorts of ways of trying to learn about the phase information. I don't know the tricks they use, but I know they're able to extract at least some of this information. Now, let me make a comment. The typical frequency that we're talking about, lambda is of order 10 to the minus 10 meters for the wavelength. From this you can calculate nu, which is lambda over c, and this gives you, well, typically 2 times 10 to the 19 hertz. Now, if you put this into frequency with a factor of 2 pi and multiply by h bar, you can get the energy. And so what you end up with is h bar omega for a typical X-ray is typically 2 times 10 to the minus 15 joules. Or if you put this into, it's approximately 12 keV. So typically, if the wavelength is the order of an angstrom, the energy is the order of 10 keV. Now that is very large compared to the binding energy of the outer electrons in a complex atom. And so from that point of view, it's a very good approximation to say these are free electrons, not bound electrons. So it's always good to check these kind of assumptions, because I'm assuming that I can treat this as free. You can make models, and this is sort of the Thomson scattering limit. If you deal with a bound electron, you get Rayleigh scattering. And you get a factor of omega to the fourth, lambda to the fourth, which comes in because you're dealing with a bound electron, not a free electron. So the assumption that the acceleration, you don't get the factor of 1 over omega squared if it's a bound electron. And so you have to work it through, but you can work at the limit, Rayleigh scattering, as well as the limit that I'm looking at here. But I assert that because the energy of the photon, or the X-ray, is large compared to the binding energy of the outer electrons, this is a good approximation. Now, how do we interpret this factor? Or this factor? Because that's the thing, that's everything we know about this is bound up in this single factor. So let me focus on that. And now let me come back to the parallel to this formula. I can erase this. We have the electron density NEL of R and T is sum on J equals 1 to N. If we have N electrons, you just get a delta function of R minus R sub J of T. Okay? And this is just the formula for the electron density if the sum runs over all electrons. And typically, if you have a metal, you would have the order of Avogadro's number of electrons in a block of metal, the order of a centimeter or millimeters on a side. I mean, the numbers you get, typically you get densities of the order of 10 to the 22 per cubic centimeter. So a reasonable piece of metal will have the order of Avogadro's number of electrons in it. And this is the formula. If you integrate this over a small volume, you get 1 for every electron in the volume, and you get 0 elsewhere. So the total number of electrons in the volume is just the number of electrons. The density is just the total number of electrons divided by the volume. So this is a three-dimensional delta function, but this is the formula that you write down in statistical mechanics. Now, what's interesting, let's take the Fourier transform of this. So if I take the integral dv e to the minus I q dot r n electron of R and T, well, again, there's a common frequency, so I can ignore this time dependence because everything's going to have the same frequency here. It just simplifies the algebra. When you get to dealing with neutrons, you have to be careful. And that's why I want to. Now, this is what I will call an electron of Q. It's the Fourier transform of the spatial electron density. But if I substitute this in here, I again get a delta function for every electron. And so you can do this integral in your head, essentially. You get sum on j equals 1 to n e to the minus I q dot rj. And so this factor here is no more and no less than the absolute value squared of the Fourier transform of the electron density. And so that's the physics is that X-rays interact with charges. Why don't the nuclei matter? Does anybody know? It's too heavy. The classical radius for the nuclei, instead of having 1 over the mass of the electron, has 1 over the mass of the nucleus. And you square that, so the nucleus is at least, even in hydrogen, is the order of 2,000 times heavier. And so you can ignore the nuclei completely in electromagnetic scattering. So electromagnetic scattering tells you all about the electron distribution, tells you nothing about the nuclear distribution. Which, I mean, you're familiar with that. And so this factor here is nothing more. This factor is just n of q for the electron, n electron of minus q. And because this, if I replace q by minus q, n electron of minus q is just n electron star of q. This is also equal to the absolute value of n electron of q as a complex number. So you get the absolute value squared just because of the properties of Fourier transforms. That if you change the sign of q, it's equivalent to taking the complex conjugate. Okay. And so what you learn from X-ray scattering is information about the Fourier transform of the electron density. Or to be more precise, you learn about the absolute value of the Fourier transform of the electron density because the phase information is stripped away in the way you do the calculation. And we also have a limitation on the allowed range of Q because Q goes between 0 and 2k sine of 1/2 of theta. So you only know n electron of Q over a limited range of Q. And if you ignore the fact that you don't know the phase, even so you can't reconstruct n electron for all space just because you don't have the Fourier transform for all Q. But it means you can calculate the long wavelength behavior of the electron density, and you get the interference effects. But to take something like a DNA molecule and crystallize it and use X-ray scattering to study its structure, that took Crick and Watson probably 10 years using a lot of X-ray diffraction patterns that Rosalind Franklin and Mr. Wilkins put together in their studies. There's a lot of skullduggery there, for some of you may know about it, which I don't want to go into. But other people have done there was another Nobel Prize for studying the vitamin B12, I think it was. There was a woman in Cambridge or Oxford who spent 10 years studying the X-ray scattering from vitamin B12. I think it was the first large molecule that they'd studied they'd been able to infer what the structure of a molecule was. I mean, these molecules have hundreds or thousands of atoms in them. I don't know. I didn't look it up. Okay. Now, if you want to study electrons in a metal, this is effectively as far as you can go because they're just spread out. And you notice I'm effectively assuming a translationally invariant system because I assume this integral runs over the whole sample. You can put it in a box with periodic boundary conditions if you like. But I'm not assuming you have a little droplet of a metal, like a liquid metal, because that's much more subtle, because that's more like studying a Bose-Einstein condensate in a trap, where you have a finite system with boundary conditions. So I'm assuming I have an extended metal, and you study that in the sense of using a translational invariance in the system. Now, the thing this is extraordinarily useful for, in addition to metals, is atoms. And so I'm going to consider a system of atoms, identical atoms for simplicity. And so the total electron density in a system of atoms can be thought of not as free electrons in a box, the way you do for metal, but you say that each atom has a particular electron density. And you use, say, Hartree-Fock theory. People have tables of what the electron density in a single atom looks like. It's not exact, but it's pretty accurate. So then you say the total electron density is the electron density in this atom plus the electron density in this atom plus the electron density in this atom. And then as these atoms move around, you assume that these shells of electrons move rigidly. So once you know the position of the atom, once you know the position of every atom in the system, you know the electron density of the whole system. But this allows you to study the fluctuations and the correlations of the position of the atoms. And that's what you do in, say, liquid argon, or liquid helium, or liquid neon, or, I just like to think of a noble gas because they're obviously very rigid. But it would also work, I assume, for liquid sodium, because I know people have done experiments on X-ray scattering from liquid sodium. And you don't treat liquid sodium, at least if it's a small droplet. Well, I'm talking out of the top of my head because I haven't thought about it. But certainly there are things where you can say, I guess for liquid sodium, I don't know whether you treat liquid sodium the way you treat solid sodium as a metal in a box, or do you treat it as, I guess you treat it as a system of atoms. I don't know. Anyway, that's beyond, I'm at the end of my supply line on that. But so now I want to say, and this is where I'm now going to take a somewhat different picture from dealing with the electron density in this form. I now want to take a different picture of the electron density and say it's made up of atoms. So I have a bunch of atoms. And the easiest one to think about is helium or neon or argon or krypton, noble gases, because they have filled shells, and so you don't get any valence electrons that play any role. But you can, I haven't thought about what happens if you do other things. So now I'm going to say, for each atom, the electron density is N0 of R if it's at the origin. So if this would be helium, you would say there are two electrons, and they're distributed in these 1s shells. But this is something you can calculate in some approximation. And if it's argon, somebody's done the work to calculate the electron density in all the different shells. Now this is for an electron at the origin. If you put an atom at the origin, if you put the atom at some position r, the electron density is just n0 of r minus r, because all I've done is shifted this atomic density rigidly. Okay? So now I'm going to talk about the set of atom positions as Rj, where j runs from 1 to the total number of atoms. Now, depending on the valence of this, there's a relation between the total number of atoms and the total number of electrons, depending on the factor z, which has to do with the total charge on each atom. And so now what I have is the electron density of R is just the sum on j equals 1 to n atom, n0 of R minus R sub j. Because I'm making the model that the electrons are bound up in these rigid atoms, and once I know the position of each atom, I know about the total density of the electrons. Okay, is that clear? I mean, it's just making a simple model that each you have a little ball of charge associated with each atom, and they're all identical. And if you know where all the atoms are located, you know the total amount of charge and the charge density in the whole system. And now we can take the Fourier transform of this. Okay? And let's see how this works out. So let me erase this. So now I can take the Fourier transform of this sum, and the trick is that I get a sum of identical terms at different positions, which allows me to simplify the calculation. This is just the way Fourier transforms work, and this is why they're so pretty. So the total electron density is a function of Q. For this particular model, I just have to write integral dv e to the minus I q dot r sum on j n naught of r minus rj. Okay, because I'm just using this expression, and I take the Fourier transform, multiply e to the minus I q dot r, and integrate. Okay? But now I can play a trick, and that's why this works, because I have the same n naught for every atom. So I can define r prime is r minus rj, or if you like, r is rj plus r prime. Now, the integral over v is a three-dimensional integral over r, but that's just a linear shift, so I can write this as an integral over v prime. And this is n naught of r prime. So I get this n electron of q is integral dv prime e to the minus I q dot r prime n naught of r prime. And now I'm left with this sum on j, e to the minus I q dot rj. Because of this factor, when I put this into the exponent, I get this extra factor. Now this sum is totally independent of this integral, because all the j dependence is here. And this factor is no more no less than the Fourier transform of the charge density in a single atom. Okay? Because this is the charge density in one atom, and this is just the Fourier transform of that. And I can write this as n naught of q times this sum. Okay. Now, if you're given a Hartree-Fock distribution of electron charge in a single atom, you can do this integral numerically. And you only have to do it once because you're all dealing with the same atoms. So this is something you in principle know all about, and now you have all this interference effect from the position of all the atoms, not the individual electrons. And so the beauty of this approach is you end up with information on the position of the atoms. This is really what you do in X-ray crystallography when you have things that don't have conduction electrons. If you have a dielectric, this is what you're interested in because it tells you about the position of the atoms. Now, real X-ray crystallography is vastly more complicated because you have molecules made up of zillions of atoms of different types, all arranged in, I mean, think of DNA. It's formally only a few different elements, but the arrangement is the most interesting thing, and so that makes it very complicated to disentangle it all. That's why I'm focusing on something like liquid argon or liquid helium, because at least you can get your mind around it and think about it. Okay. Now, this quantity n naught of q has some very interesting features. So let me study it a second. What is n naught of 0? If I say q equals 0, what is this integral? Well, you just get the volume integral of the charge density of the electron, the charge density of the atom, which is just the capital Z, Z. It's the valence. So this is just equal to the atomic number of the atom. And so this n naught of Q divided by n naught of 0 is just integral dv prime e to the minus I q dot r prime n naught of r prime divided by capital Z. Okay? And if Q is equal to 0, this is just 1, but typically because this is an interference effect, typically this factor will be less than 1 if Q is non-zero. And this factor is typically called F of Q. It's called the atomic structure factor. It tells you about the Fourier transform of the charge density in a particular atom. And here again, I'm simplifying because I'm assuming that we're only dealing with an assembly of single atoms, all the same species. You can generalize it, but it's harder. And this in general is complex because this is in general a complex thing. Now when you take the absolute value of this whole thing, you're going to get the absolute value of F. And so at the end of the day, the interference effect, I can write this factor here as Z F of Q times this sum on J e to the minus I Q dot Rj. And so when I take the absolute value of the square of this, I get Z squared times the absolute value squared of this times the absolute value squared of this, which tells you about the interference from the different atoms. Now, the absolute value squared of this is just a factor. And so let me write it down because it's got some interesting features. NEL of Q, absolute value squared, the square of this is just Z squared F of Q squared times the absolute value sum on J over all atoms e to the minus I Q dot R sub J squared. Now, this is actually a very familiar structure. If you think about a diffraction pattern from a grating, or a two-dimensional grating where you put a lot of holes in, the Fourier transform of that, which is what comes into the diffraction pattern, involves two factors. One that tells you about the spacing between the slits, or the spacing between the circular holes, or whatever you've done, and it's multiplied by a factor that tells you about the diffraction by a single hole. If it's a slit, it's the one-slit diffraction pattern. This is the analog of the one-slit diffraction pattern from a single atom. This tells you about the arrangements of all the different atoms. So it's just the same physics as diffraction from a grating. And I assume you're all familiar with those. You get the product. Usually you don't worry so much about the wings of the single-slit diffraction. You're more interested in the interference between the whole bunch of slits, which gives you the n-slit diffraction pattern. But typically the wings fall off because the single-slit diffraction pattern goes like this. And so the central pattern, you get this n-slit diffraction, but far off in the wings, it's modulated by the shape of the single-slit diffraction pattern. You can go back and look at book on optics. So the net result, if you really do the quantum mechanics of this carefully, is you get an average of sum on J e to the minus I Q dot Rj absolute value squared. And you can either think of this average as a quantum mechanical average over an ensemble of states in thermal equilibrium, or if you're doing a classical calculation, these would be over a canonical ensemble or a grand canonical ensemble, depending on the kind of system you're studying. But so I'll use this angular brackets to represent an ensemble average without trying to be too specific about exactly what it means. So ultimately, the basic conclusion is that X-ray scattering measures an ensemble average of this kind of quantity where this represents the position of all the atoms. And now let me play the same game. So I'm now going to introduce an atomic number density, not an electron density. And so I'm going to say n atomic of R is sum on J equals 1 to the number of atoms, a delta function of R minus R sub J. So this is completely parallel to the behavior for a set of electrons, except now I'm saying all I'm focusing on is the position of all the atoms. Okay? And the Fourier transform of this is n atomic of Q is just sum on J n atomic e to the minus I Q dot Rj. So this is really just the same as the ensemble average of n atomic of Q absolute value squared, like that. And so what you end up with is the ensemble average of the atomic densities, the Fourier transform of the atomic density. And now, if you make a leap of faith, you can actually come back and try to write this in terms of the spatially dependent atomic densities, because this is just a Fourier transform. And so now let me write this in the following form. Again, this is just manipulation, if you like. So I'm going to write this as an atomic of Q and atomic of minus Q ensemble average, or I could write this as an atomic of Q and atomic star complex conjugate of Q ensemble average. So what we end up with is a correlation function of two densities, or a density and its complex conjugate, but each of these is a Fourier transform. And so now let me write this in the following form. So I can now write this as a double volume integral, integral dv dv prime. I get e to the minus I q dot r, e to the I q dot r prime, because of the minus q of the complex conjugate, times the correlation function n atomic of r, n atomic of r prime ensemble average. And the important feature is this is manifestly real, so all the complex conjugate just goes up here in the exponential. Because the atomic number density can't be a complex number if you're dealing with it in coordinate space. And this is called the two-body correlation function for atomic densities. So this is what you try to measure by using X-ray scattering for liquid neon, say. What you're interested in is knowing if you have an atom at this point, what is the probability that you'll have another atom at a distance r away? And that's called the structure factor. And so this is what people try to study liquid, non-conducting liquids. They try to study the density-density correlation function between the different atoms. Now, so basically what you end up with from X-ray scattering is this two-particle correlation function, or the density-density correlation function, but it's always at a single time. And that's where the neutron scattering turns out to be much more interesting, much more powerful, because you end up with correlation functions at different times as well as different positions. Now, the usual picture is we have an extended medium. So this function, if you have a huge box like this, the assumption is that if you're away from the edges, this only depends on the difference of r and r prime. Because it doesn't matter whether you put your origin here or put your origin here, as long as you stay away from the edges. And so you can always, by taking the system sufficiently large, you can ignore edge effects, and you use the fact that this really is a function only of r minus r prime. And that allows you, that's translational invariance, and that's the trick the reason Fourier transforms are so powerful in many-body physics is that you use this translational invariance to argue that functions that really look like they depend on two separate variables only depend on the difference. And so the Fourier transform, you get I to the iq dot r minus r prime. One of these factors just gives you a trivial factor of the volume, and you reduce it to a 1 Fourier integral instead of 2. That's why the translational invariance is so powerful and so important. Now, it's a trick, but it's a very useful trick for macroscopic systems. And again, to come back to the Bose gas in a trap, that's where you can't use this trick because they're spatially non-uniform. You can't say that it doesn't matter where you put the origin, because if you put the origin at the center of the trap, you get a very different picture from putting it halfway to the edge. And so those are the subtleties. That's why the many-body physics, that's why nuclear physics has been so difficult, because you're dealing with many-body problems involving, say, a couple of hundred nucleons at most. And they're not translational invariants. You have to use the angular momentum decomposition. And you end up with all these horrible Clebsch-Gordon coefficients, which are messy, to put it mildly. So now we make a model again. And now I'm going to assume that there is some average density. This is the average, and this is uniform. And that holds for a liquid as long as you stay away from the edges, and it holds for a solid as long as you stay away from the edges. And then you can say that n atomic, which depends on r, because this fluctuates violently every time you come close to an atom, on the average is n atomic. This is the average value, plus what I'll call n tilde of r, n tilde atomic. And this is the fluctuating part. Now, although this is strictly a sum of delta functions, you know that you often coarse grain it. You treat it as a sort of smooth function. And what we're interested in is, as I say, given the fact that you have an atom in one place, what's the probability of finding another atom a given distance away? And that's called the atomic, the structure factor. By definition, if you take the average of this, you see that the average of n tilde has to be 0, right? Because the average of this is this average, and this has to have 0 average. Because if you look at the average of all the fluctuations from the mean, you're going to get 0 for the fluctuations. But, and now this is what's interesting, we're looking at this correlation function which has two things in it. And so when you take a two-body correlation function, what you're going to end up with is the correlation of the fluctuations. So strictly speaking, n atomic of r and atomic r prime, you get this average and atomic average squared, which is uniform, plus, because of this fact, the cross terms drop out, and you end up with n atomic at r and atomic at r prime. Okay? So this is something you can calculate. And so what you really end up with, the most interesting part of this, is the correlation function of two density fluctuations. And that's the result. That's what you really work for to understand. Now, if you come back and take the Fourier transform, the inverse of this, the Fourier transform of this is a Fourier transform of constant, which only contributes at q equals 0. And so at q equals 0, you're talking about forward scattering strictly, and you really can't measure that because you have an incident beam. You have to be a little distance angle away, otherwise if you look, you're just going to be blinded by the incident beam. So the q equals 0 part is effectively irrelevant, where it's not measurable. And so at the end of the day, what we really end up with is this. The physical quantity is always typically the Fourier transform of this fluctuation will be n atomic tilde of q. And what we really end up with is n tilde, the fluctuation, the Fourier transform of q n tilde atomic minus q. And this is what you end up with, or you can write this as n atomic of q, n atomic of q star. And because you've taken out this q equals 0 part of the Fourier transform, this actually converges for large q. This doesn't diverge. And this correlation function, because you're talking about fluctuations, this goes to 0 for large r minus r prime. This original thing would just go to the mean value squared, but you've taken that out, so this converges, and so the Fourier transform of this for large r and r prime gives you a convergent answer. And apart from numerical factors, this is what's called S of q, the structure factor. So you define S of q as, let me write this down. This just details, but this, you'll see this mentioned a lot, is 1 over the mean density times the volume integral dv e to the minus I q dot r in tilde of r and tilde of 0. And now I've used the translational invariance to say that this is really only a function of the difference of the two variables. And this is the thing that converges for large r. So this Fourier transform converges. It's conventional to put in this factor of 1 over the number density, and that's what's called S of q. And if you look in books on liquid noble gases or other things, what they give tables of is S of q. And S of q, just to be simple, it has, at q goes to 0, it goes to 0 typically. It comes up, it has a peak, and then it oscillates like this as a function of q. And this q value of the peak occurs at typically 1 over the interparticle spacing, call it d, in the liquid, interatomic distance. And the fact this has a peak associated with the mean, if you have things like this, little spheres, supposed to be a liquid, so they're all random. They're not periodic like that. But if the distance between these is of order d, then typically this has a peak at order 1 over d because of the interference. It says that if you have a particle at the origin, the most likely position of the other particles is nearby will be the order of the interparticle separation. And when you take the Fourier transform of that probability, you get a peak associated with 1 over d. So the factors of 2 pi you can worry about, which is not a trivial factor, but it's all, you can do it all numerically. And you can invert this to infer what's called g of r, which is the two-body distribution function, which is a probability that if you have a particle at the origin, what's the probability to have another particle nearby? And the physics is that if you go to very close distances inside the hardcore radius, then the probability is 0. So g of r looks kind of like this. G of r would be this thing. I didn't plot this out, but g of r looks roughly like this, and it again oscillates as a function of r. And this would be the hardcore diameter if you treat these as hard spheres. Because if you have a particle at the origin, you can't have this closer than twice this distance, or the diameter, not the radius. Okay? So these are words that you use a lot in studying liquid helium. And the fact this has a peak will turn out to be very important in an argument I hope to give you next time that Feynman invented about the distribution, the behavior of liquid helium measured by X-ray scattering and also by neutron scattering. So as I say, my conclusion is that everything you measure here comes down to this factor if you have a liquid made of atoms that don't have conduction electrons. And now next time I want to talk about the comparison with neutron scattering. Neutrons are very different because they don't travel at the speed of light. You're talking about cold neutrons. you make them cold enough so their wavelength, their de Broglie wavelength, is the order of an angstrom. But when you do that, the energy of the neutron is very small, and I'll write it down next time. And so you can actually, if the neutron scatters, you can study the recoil energy of the neutron, how it differs from the incident energy, which you can't do for the X-rays. And so the fact that you have energy resolution and momentum resolution for the neutron means that ultimately you end up with space-time correlation functions of density fluctuations. And that's how you measure the phonon distribution function in crystals. And that's how you measure the famous excitation curve for liquid helium, because you use neutron scattering, which has energy resolution as well as frequency, as well as momentum resolution. And so I want to go through that in some detail next time. You'll see it's actually rather parallel to this, but the fact that you have energy resolution means you have to get frequency Fourier transforms as well as spatial Fourier transforms. But it all works out in a very similar way. And from the measured quantity that you get from neutron scattering, you can also come back and measure this quantity by doing some integrals. And so you can compare the results for X-ray scattering and neutron scattering. And they better agree, and they do, because otherwise I wouldn't be talking about it. But it's a nice coherent picture of these correlation functions, and it shows you why correlation functions play such a central role in trying to understand many-body physics, both at the electron level and at the atomic level. So let me stop here. I'm happy to answer any questions. Thank you.
When you have a very dense and very strong correlated systems, such that I can't imagine that the electron is localized like you start with. What's happened then?
That's a very good question. I mean, this is the crux of the matter of what are called highly correlated electron systems, like the Mott insulator, or the high TC superconductors,
Like that?
or strontium ruthenate, or heavy fermions, all of which, I mean, these are the systems that everybody is struggling to understand, and there are almost as many theories as there are theorists, and there really aren't any. I mean, the Mott insulator, I think, is pretty well understood.
But where that breaks, I mean, because I cannot localize? I cannot consider the n is 0 for each atom in the beginning? That's where the thing breaks down?
Well, yeah, I assume that you can't. I mean, I made a model that each atom is inviolate. And if you try to squeeze atoms, I mean, the story is, it's never been seen, or probably hasn't been seen. If you put hydrogen under multiple megabars, it's supposed to become a superconductor in which the electrons are superconducting because they cease to be bound. Now, there have been a lot of theories of that, but I don't think it's been seen conclusively. Certainly, there are systems that are insulating at normal pressures, but if you squeeze them hard enough, they become superconducting. And presumably, the electrons cease to be bound on the crystal and become conduction electrons, which then have the phonon mechanism of BCS that binds them together, forming Cooper pairs. So I'm not an expert in that. I can't give you examples other than this example for hydrogen. But I mean, Mott actually used the hydrogen as one of his theoretical pictures, because you start with the electron, each electron is bound to a proton, but if you squeeze them hard enough, the pressure effects become sufficiently large that at some point it becomes favorable for the electrons to become unbound and become these so-called highly correlated electron systems. And that's predicted to take place at, I don't know, millions of bars. I don't know what the numbers are. Do you know, Chris? Have you ever studied this? Neil Ashcroft has spent a lot of his life just trying to do theoretical calculations on that, the co-author of Ashcroft and Merman. It's one of his interest specialties. But it certainly has been seen for other materials, where if you pressurize them.
I guess the question was whether these phenomena can be accommodated in this two-point correlation function or not.
Well, you'd have to go back to the original electron description. There'd be a total change in the character of the the two-point correlation function described in the individual electrons would have a very different character if you undergo this sort of correlated phase transition. So what I've done when I do this is atomic densities. I'm making a very simple, almost childish model just to introduce you to the ideas, but that's clearly going to break down if you get to a highly correlated limit, in which case you've got to do much more work. And I mean, the high TC materials are very complicated because they're not isotropic, they're crystalline, they're complicated. So all the assumptions that I've made here, you have to start from very scratch and work it all out all over again. And I suspect if you put, well, liquid helium, when you pressurize it, it eventually becomes a crystal. I don't know whether all these systems crystallize or whether some of them, the electrons delocalize, the outer electrons delocalize, and you get a different system. Again, I'm just not an expert on this.
Simple example would be molten metals.
Yeah.
For instance.
Yeah, I mean, because the molten,
Competition can be localized and extended at the same time.
I mean, if you take molten sodium, the question is, do you think of it as sodium atoms, or do you think of it as the ionic cores plus a conduction band of the single outer electrons? Or, I mean, I guess other kinds of things is H2 molecules where you crystallize them and put them under pressure. And they're all, I know there's some various phase transitions, I don't remember what they are, but all these kind of things have interesting phenomena associated with it. So that's why this question of highly correlated systems at low temperatures is so interesting. And the transition between these two regimes is called a quantum critical point. And so you get these quantum phase transitions between them because they're not mediated by thermal fluctuations, but by presumably quantum fluctuations in a way that isn't really well understood, to my knowledge. I mean, people talk about it. They have sort of schematic diagrams, but I don't know. I'm sure they're one-dimensional models where you can study all this. But when you go to 2- and 3-dimensional models, it's much more complicated.
Just a small comment to these strongly correlated systems. As far as I understand, such formulas can be derived in a very general level, and the problem with strongly correlated systems is not the formula itself. It can be okay, but people do not know how to calculate correlation functions. It's a technical problem, not knowing how to calculate them.
And it's hard to and it's hard to measure them too.
Oh, yeah. So formula is okay.
Okay, other questions?
Question, Provost. No more questions.
Okay.
So we meet again at 9 o'clock tomorrow.
Okay,
And so thank you again.
thank you.